Right, y'all. Probably the last video for tonight. We'll review the Gram-Schmidt process since it's related to the spectral uh, uh, theorem process. So let's see what we have here. We'll be looking at this part of the book. It'll be basically in uh, chapter 4, section 2, orthogonal bases, which is apropos since we're talking about making an orthonormal basis. Okay. So this is a bit of a technical issue. We'll load this again. Right, so we have chapter 4.2, Gram, like the unit, Schmidt. Right, so the Gram-Schmidt process. So we have a basis, and the basis is a bunch of vectors that span a space. Let's say V1 through Vk. For an inner product space V, we're obtaining an orthogonal basis. So this is our orthogonal basis, W1, Wk. So this is how we obtain an orthogonal basis for V. So the first vector in the orthogonal basis is the vector from the other basis, as we saw in the last video. The second vector in the orthogonal basis is the second vector in the original basis minus the projection of the second vector of the onto the first vector of the second vector. So I do remember this from one of the classes. So that's projection. So that's going to be V2 dot W1 over the magnitude of W1 squared and W1. So whichever one is being projected onto has everything like that except for the one. And then the third vector is going to be V3 minus the projection onto W2 by V3. So it's going to be V3 minus V3 dot W2 over magnitude of W2 squared W2, and so on and so forth. So we have a basis. This is how we can make another vector that's orthogonal to the basis that we have. Simple enough. So let's do an example, and we'll call it a night. So we have I'm going to call it x1 equals 1, 1, 1, 1. X2 equals 3, 1, negative 1, 1. And x3 equals 1, 1, 3, 3. We want to use the Gram-Schmidt process to find an orthogonal basis for V for that span, right? So we have orthogonal 1 equals x1 minus the projection. No, the first one is just the first one. So the first one is just 1, 1, 1, 1. The second one is going to be the first one minus the projection um, onto the second one of the initial first one, W1 minus V1 dot W2 over magnitude of W2 squared W2. I'll make sure I did that right. So everything's right except I switched the numbers. So this is 1 and this is 2. So you're taking the second one and projecting it onto the previous one. So this is 2, 1, 1, 1. And this is actually V2 as well. So still trying to work out a good pattern. And actually this continues minus projection onto W1 of V2. So that's a minus V2 W1 and so forth. So this will be W3 equals V3 minus the projection onto W2 of V3. So that equals, oh, and I got to do the additional one, minus the projection onto W1 of V2. Now the V will always be the third one, but it moves through the other ones. So it's going to be V3 minus V3 dot W2 over the magnitude of W2 squared W2 minus V3 dot W1 over the magnitude of W1 squared W1. right? So let's spread out what this is going to be. So W2 equals, that's 3, 1, negative 1, 1, minus 3, 1, negative 1, 1, dot, actually, so working on this one here, 3, 1, negative 1, 1, dot, one, 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 over 4, 1, 1, 1, 1, and W3 equals, so that's going to be 1, 1, 3, 3, minus 1, 1, 3, 3, dot, crap, I gotta get the second one first. It's going to be 3, 1, minus 1, 1, minus 3 plus 1 is 4, minus 1 is 3, plus 1 is 4, so that's 1, 1, 1, 1, 1. So that's going to equal 2, 0, negative 2, 0. And that's what they got. So W3 is going to equal, now we're doing V3, 1, 1, 3, 3, minus 1, 1, 3, 3, dot 2, 0, negative 2, 0, over, that's the square root of 2, that's 2 squared plus 2 squared, 4 plus 4 is 8, so that's going to be 8. And 2, 0, negative 2, 0, minus 1, 1, 3, 3. So the V3 carries over. That's the one that we're transforming. Now we go to W1 over 4, and the W part is the predominant. So it's going to be 1, 1, 3, 3, minus 2 plus 0, minus 6 plus 0. So that's negative 4. That's plus 1/2, 2, 0, negative 2, 0, minus this 1 plus 1 plus 3 plus 3, 8 over 4, that's 2, 1, 1, 1, 1. So that's going to be 1, 1, 3, 3, plus 1, 0, negative 1, 0, minus 2, 2, 2, 2. So that's going to equal 1 plus 1, that's 2, minus 2 is 0. 1 plus 0 is 1, minus 2 is negative 1. 3 minus 1 is 2, minus 2 is 0. And 3 plus 0 is 0, minus 2 is 1. Did they get that? 0, negative 1, 0, 1. They got that. So that's how we get the orthogonal basis. So W1 equals 1, 1, 1, 1. W2 equals 2, 0, negative 2, 0. And W3 equals 0, negative 1, 0, 1. And all we have to do is divide each by the length of each to get to normalize each one. And then we can put it into a matrix to get the orthonormal matrix. Right, so I'm going to have to practice that, but that's the process to apply the Gram-Schmidt to get an orthonormal basis if we have a basis, or at least an orthogonal basis if we have a basis. So we have a basis, but it's not orthogonal, it's just a basis, but it spans all dimensions of the space. We can do this to not only span the space, but make each basis orthogonal to each other, each basis vector. So I'll be back tomorrow. We'll continue this, have an exam on Thursday, so I'm preparing for it. And we'll make sure we get an A. See y'all next time.
On Battlestar Galactica.